Welcome to Trane Engineers Newsletter Live program. In today's program, we're going to take a closer look at the acoustics associated with outdoor HVAC equipment. In most cases, there are one or more components of a system outside, such as rooftops, air-cooled chillers, and cooling towers. And very often this equipment radiates sound. And when that sound causes problems or is unwanted, it becomes noise. Last year, we developed a program on sound data, how it's generated, and how to determine good data from the bad. And building on that discussion in this hour, we'll provide you with information that will help prevent noise problems associated with HVAC equipment. But we can't turn you into acoustical consultants. So by the end of this program, you should be able to distinguish between the simple sound analysis we'll be showing you is acceptable and when the job requires a more sophisticated analysis done by an acoustical consultant. To start, we're going to talk about local sound targets commonly found, the source path receiver model, and complications. And later in the program, we'll talk about attenuating outdoor applications and the usage of an acoustical barrier. Today, we have Trane application engineers Dave Guckelberger and Eric Sturm. I'll be asking Dave and Eric a series of questions to take us through this topic. So let's get started. Eric, how do we know if we're going to even have a noise problem?
Technically, the distinction between sound and noise is based on perception, but there are also non-subjective measures. The United States Environmental Protection Agency describes noise as sound that, quote, interferes with normal activities such as sleeping, conversation, or disrupts or diminishes one's quality of life. Noise is unwanted sound. For outdoor acoustics, local ordinance is likely the most common non-subjective measure to set sound levels. States and jurisdictions have the ability to create their own ordinances, so there's a lot of variation in how they're written. Typically, they will list a maximum sound pressure level measured at the lot line. Here's an example lot line sound ordinance from Portland, Oregon. First, the ordinance describes the property line, or lot line, as the boundary. Next, it divides the day into day hours and night hours. Finally, a table is displayed with various A-weighted sound pressure levels for the source and receiver zoning categories. In this example, the night hour sound levels must be 5 dBA lower than the day hour levels. Some jurisdictions will provide maximum sound pressure levels in octave bands. Here, the city of Cambridge, Massachusetts has defined maximum octave band sound pressure levels from 31.5 to 8,000 Hertz for several zoning classifications, including residential, residential inside industrial, commercial, and industrial. Like Portland, they've also designated equivalent dBA levels in daytime and nighttime hours. The variations go from a single dBA level to different levels for day and night, to maximums by octave band, to specific restrictions on tonal or impulse sound. Oftentimes, compressors are the source of tonal noise and have objectionable sound quality. It's critical to know the details. Alternatively, the maximum sound level may be determined by a site requirement. An example is a school. Here, we know the maximum acceptable sound level inside the classroom. That, combined with the transmission loss of the walls and windows, allows us to determine the maximum sound level outside of the classroom. This can provide a target for how much sound can be generated by equipment outside of the school. So the goal of our prediction is not to prevent noise complaints per se, but rather to meet a preset sound target. Regardless of whether the desired sound level is set by ordinance or a site requirement, it's an important component of the source path receiver model.
So it sounds like one of the first steps for sound-sensitive jobs would be to identify and understand the relevant sound ordinance. Source path receiver model is next. Dave, could you explain what this is for people that might not be familiar with the terms?
Source path receiver describes the three important components of an acoustical model. In simple terms, source is what creates the sound, receiver is the location where the sound will be measured, and path accounts for everything that changes the sound as it travels from the source to the receiver. Eric just described one important part of the receiver, having a specific acoustical target. It doesn't matter if the target is a single A-weighted value or specific octave band levels, just as long as everyone agrees on the target. The other part of the receiver that everyone must agree upon is the location. For a lot line ordinance, we look for the worst case point on the lot line, which is generally the point closest to the sound source. However, it's important to remember that lot lines extend vertically, so height of the measurement must also be agreed upon. The slide shows an installation where the edge of a building blocks some of the sound that would be heard by a person located at ground level. But our measurement at a second-story window of a neighboring building would be higher than the ground level value. Generally, sound ordinances must be met anywhere outside the property line, regardless of the height or distance from the property line. High-rise buildings, where the receiver is above the unit, causes an additional concern. Sound test standards for air-cooled equipment don't fully account for sound radiated straight up from the unit. When the source and receiver are basically at the same level, it's not an issue. But when the receiver is looking down on the top of the unit, additional sound should be considered. It's also important to understand ordinance wording. Most state that the measurement is taken at the lot line, but some say at the neighboring property, which creates some ambiguity as to where the measurement is taken when a street or other public space separates the two properties. Other ordinances state that the measurement is taken inside the window of a neighboring property. And in areas where significant background sound already exists, you'll need to determine how that sound will be taken into account. The key takeaway is that you know where and how the measurement will be taken when selecting your receiver location. Key attributes of the source are sound data and unit configuration. Sound data is the foundation of the acoustical model, so inaccurate sound data translates to an unreliable prediction. Unit configuration includes the shape and size of the equipment, the type of sound sources, and where they are positioned on the unit. For the equipment shown, fans, compressors, and the structure of the unit are all unique sound-emitting areas. The details of each become important when attenuation of the unit is required. Sound data for the unit might also include directivity information. The location of sound sources and structure of the unit can result in more sound radiating from one side and less from the other. Rotating the unit so that the quiet side faces the receiver can reduce sound in the area of concern. And finally, the term path is used to describe the environmental effects that change the sound as it travels from the source to the receiver. Each job has a unique sound path that must be accounted for in the acoustical model. Fortunately, several equations have been developed to account for the environmental effects.
So source includes the equipment specifics, receiver includes the target specifics, and path refers to the calculation portion. Lot line sound ordinances don't directly limit equipment sound, but they do establish the sound target. And I think another key takeaway is that the receiver portion includes both the target sound level and the receiver location. Picking the correct receiver location requires knowledge about the site, including the neighboring buildings. So Eric, how about an example to show source path receiver modeling in practice?
Here's a simple example in plan view. Typically, the application is not this straightforward, but we'll start here and add some complexity as we go. The site plan shows a school served by an air-cooled chiller, the source. The chiller is located on the outer edge of the parking lot to avoid noise problems at the school building. A set of practice fields separate the chiller from the street and the adjacent neighborhood. We have sound power and dimensional data for the chiller. The local ordinance requires the sound not exceed 55 dBA at the lot line, which is 190 feet from the unit. This is where the receiver would be. The outdoor distance correction equation for a flat plane free field environment works very well in this case. Nothing surrounds the unit and the area is flat, making this a simple distance correction. The equation is used to convert sound power, L sub W, to sound pressure, L sub P, at a distance, D. The difference, or correction, between the sound power and pressure would be computed for each octave band and weighted to produce a single A-weighted number. So Q is the directivity factor that accounts for how sound radiates in different environments in the equation. When sound radiates from a point in space, it expands as a sphere in all directions. All points on the sphere are equidistant from the source, which will have the same sound pressure as shown here in elevation view. When the sound source is placed on a flat plane, like the Earth in our example, the sound has half the area available to radiate. Since the same sound energy is radiating from the source, but it only has half the space at a given distance, the sound energy is double what it would be for that distance for spherical radiation. Sound sources can also be placed in an environment that resembles a quarter of a sphere, like a chiller near the wall of a building, or when placed on the inside corner with 3 reflecting surfaces, the ground and 2 walls, an eighth of a sphere. So let's use this in our example. Since the chiller is on a flat plane, the Earth, we'll use a directivity factor of 2 and compute the correction with a distance of 190 feet. Plugging the numbers into the equation tells us the sound pressure at this distance is 42 decibels less than the sound power. The result is applicable to all octave bands. We simply subtract the correction from the octave band sound power data, and the result is a distance-corrected sound pressure. You can see this in the 3rd row of the table. When the computed sound pressure is A-weighted, the result is 58 dBA, which is slightly higher than the lot line requirement. Let's come back to this later.
Sounds good, Eric. So when using that distance correction equation, a Q value of 1 is not going to be very common. Instead, the factor will be a function of where the source is placed. The process seems pretty easy. Simply plug the sound data and distance into the equation, and we have an answer. So how accurate is this prediction?
Well, it depends. We chose the details of this example to avoid complicating factors. There are many things that can reduce the accuracy of the prediction, and we need to talk about those because if we ignore them, they can result in a big miss. The first concern is the sound data for the unit. An error in sound data translates directly to an error in the prediction. Also notice that the equation Eric used converts sound power to sound pressure. Sometimes unit data is only available as sound pressure. Don't use the equation when the unit data is in sound pressure. And it cannot be used to convert unit sound pressure back to unit sound power. For outdoor equipment, look for sound power data taken in accordance with AHRI 270 for small units or 370 for large units. But even if the unit sound power data is accurate, you need to consider the operating point of the unit. Acoustical data, measured in accordance with the appropriate AHRI standard, is recorded with the unit running at a specified performance condition. Typically, this is full load, and full load is often the loudest operating point. But for some units, they're louder at part load or ambient temperatures that differ from the test condition. If that's the case, the increase in sound will not be included in the prediction. For a very strict sound requirement, I would want a couple dB clearance between the prediction and the target to be safe. Secondly, the equation used in outdoor sound prediction is based on theoretical analysis. Several assumptions are made to simplify the equations and make them practical for general use. When the assumptions are valid, the results are good. So it's important to have an idea of when we are violating the assumptions. The first assumption is that the sound radiates from a point in space. When sound radiates from a point, it expands directly away from the point. The sound energy is spread evenly over the surface of a sphere. So at a given distance from the point, regardless of the direction, the measured sound will be the same. This creates a uniform sound field and makes it simple to model how the magnitude of the sound changes as it moves away from the point. But that's not how sound radiates from an HVAC unit. Typically, there are several sound sources on the unit, and none of them resemble a point source. Sound radiating from each area on the unit interacts with sound radiating from other areas. You can see that even for the simple case of two adjacent sources, the consistent radiation pattern is lost. These overlapping sound waves create an unstable acoustical environment called the near field. Sound power to sound pressure estimates in the near field should not be attempted. So the equation doesn't work well close to the unit. How close is close? It's generally accepted that the equation should not be used if the receiver location is less than 2 times the dimension of the unit facing the receiver. In the range of 2 to 5 times the facing dimension, the calculated sound pressure can be as much as 5 dB lower than the actual. Predictions near the unit are one of the cases where advice from an acoustical consultant is recommended. The final assumption is that sound radiates into an acoustical free field. That's an area without reflective surfaces, other sound sources, or atmospheric and ground absorption effects. It's pretty rare to find a job where the unit is in an acoustical free field. Most of the time, the sound path between the source and the receiver is filled with things that will either increase or decrease the sound at the receiver location. Reflective surfaces behind or beside the sound source redirect sound toward the receiver location. But reflective surfaces between the source and the receiver, also called barriers, tend to block the sound and result in lower sound at the receiver. Even thermal gradients and atmospheric absorption can affect the sound, but these are generally ignored for distances less than 500 feet.
So accurate sound data is important, but even when the sound data quality is good, it may not match the sound produced by an operating unit. And the distance correction equation only works in a simplified scenario. Is that right?
Well, it's not quite that bleak. The Q factor in the sound power to sound pressure conversion equation can account for some reflective surfaces. And we have an equation that predicts the attenuation provided by an acoustical barrier. The takeaway here is that real-world conditions add complication that must be considered. That means the accuracy of the equations is diminished, but it doesn't mean that the calculations are useless. The thing to remember is that as complicating factors increase, so should the buffer between the prediction and the target. For the simple example that Eric described, I would expect these equations to work quite well.
Eric, can you talk about how reflective surfaces and barriers add complication and explain how they're accounted for in the prediction?
In the example I showed earlier, the chiller was located between the parking lot and a practice field, which essentially placed it in an acoustical free field. In most cases, HVAC equipment is placed near the building to facilitate utility connections. The simple case of a sound source placed very near a large, flat surface can be accommodated by changing the value of Q to 4. This models the building as an infinite flat plane, which is a good assumption if the building is large compared to the equipment. For shorter or narrower walls, some sound will go over and around the building, reducing the sound headed toward the receiver. In most cases, this can be ignored. As equipment is moved away from the building, the reflected sound contribution is reduced. In this case, the reflected sound has to travel farther to reach the receiver. It has to travel to the wall and then back to the unit before it's added to the direct unit sound. One way to visualize this extra distance is to think of the reflected sound as a second sound source located behind the original sound source by twice the distance to the wall. Oftentimes, a barrier is used to deflect or block noise from reaching the receiver. When a barrier is inserted into the example, some sound is reflected away from the receiver and the resulting sound pressure level at the lot line is lower. So we have pretty good methods for accounting for reflective surfaces located directly behind the equipment, but reflective surfaces in other locations are more challenging. Examples of these include other buildings, solid fences, and other pieces of equipment. Dream, if you can, a courtyard. This photo shows a real-world situation that would be more difficult to model. Here, the reflective surfaces are not very tall, and the chiller's kind of in a corner, but not really, and there are many other reflective surfaces. This is pretty far from the flat plane used to calculate reflection and warrants additional caution.
I'd like to understand how much impact these surfaces have. It's clear that real-world conditions vary from job to job, and real-world conditions aren't the same as those assumed by the model. But is there a way to quantify how much impact reflective surfaces contribute?
The best way I've found for quantifying the impact is to bracket the answer. Suppose we want to model the HVAC unit shown in the picture Eric used as an example of a complicated acoustical environment. Our lot line of concern is 100 feet across the parking lot to the right. The chiller sits in front of a multi-story building to the left of the picture that is acting as a reflective plane. Plus there is a small single-story structure that sticks out from the building. The picture on the bottom of this slide shows a schematic version that only accounts for the tall building. We know that sound will reflect off the tall portion of the building, and we can account for that with a reflective surface. The model for this arrangement uses a reflective plane behind the unit as shown at the top of the slide. Suppose we model it this way, and the result is 50 dBA at 100 feet. But we know this model is underpredicting the sound at the lot line because it doesn't account for the reflection from the small extension. We can change the model to account for the small single-story extension. The schematic view at the bottom shows a representation of both the main building and the small extension. The model for this arrangement consists of two infinite reflecting planes as shown in the plan view at the top. Essentially, this changes the value of Q in the equation from 4 to 8. When modeled with the second reflective plane, the calculation result is 53 dB. That's 3 dB higher than the first prediction. The problem with modeling the small extension as a full plane is that at the job site, some sound will go over and around the small extension, reducing the sound that reaches our receiver. So neither of the two models does an accurate job of predicting the sound at the receiver. The first is too low, and the second is too high. The correct answer is in between. But notice that the sound estimates only differ by 3 dB, so we have established a pretty tight range for the estimate. If there are no other sound source or path components to consider, we can compare our estimate to the sound target. If our high estimate is below the target, the prediction meets the sound goal. If the low estimate is above the target, a change to the source or path will be required. And if it happens that the two estimates fall on either side of the sound target, then we have to make a judgment call as to which of the two predictions is closer. In the complicated acoustical environment shown in the original picture, I would want both estimates to be below the target. If that can't be done with simple changes, this level of complication is a good reason for getting an acoustical consultant involved.
That makes sense. Each time a limiting plane is added, the sound has half as much space to radiate into, which doubles the sound going into the available area. And double the sound energy translates to an increase of 3 decibels. But real-world conditions don't mimic the infinite planes used in modeling, so the judgment and experience of an acoustical consultant is a benefit for complicated scenarios. Okay, now that we can make a reasonable estimate of the sound at the lot line or other target location, Eric, can you explain what can be done if the estimate comes in over the allowed sound level?
At a high level, there are two choices: quiet the source or quiet the path. Check with the manufacturer to see if there are quieter versions of the equipment. Sometimes manufacturers will use mufflers, quieter fans, compressor wraps, or other attenuation measures to lower equipment sound. When units are factory rated with and without sound attenuation, it's easy to determine how lot line estimates will change. Here's an example of a unit that comes with 2 attenuation options. The chart shows A-weighted sound pressure at 30 feet from the unit in the various configurations. For the 180-ton unit, the superior option drops the sound 4 decibels, and the ultimate option drops the sound up to 13 decibels. These drops would translate through to the lot line. When looking at attenuation options, it's important to remember that sound isn't added on a linear scale, it's logarithmic. To put this into perspective, if 2 identical units are running and one is turned off, the result would be a 3 decibel drop. But to get to a 12 decibel drop, you would need to have 16 equal units running and turn all of them off except for one. This data is sound pressure, which means the equation used earlier would not apply. To use that equation, we need sound power. Fortunately, the manufacturer also provides sound power for the various chiller configurations. So let's return to the air-cooled chiller and lot line analysis. With the standard chiller and no factory attenuation, we were at 58 dBA, and the goal is 55. I reselected the chiller with some factory sound attenuation on the suction and discharge lines, and with quieter condenser fan operating speeds. The resulting sound power is entered into the second row of the table and corrected for distance again. The resulting A-weighted value is 55 decibels, which is right at the lot line requirement. It might be too close for comfort. So factory options are preferred because of the tested sound data. But if the unit is already in the field or factory attenuation options aren't available, field modification may be the best option. When applying treatment to the unit in the field, remember that units may have more than one sound source. In most cases, the HVAC equipment manufacturer won't have sound data to show the contributions of individual components. For example, suppose the unit has fans and compressors with an enclosure to quiet the compressors. Without knowing the relative contributions of the compressors and fans, there is no way to know how much the enclosure will reduce the total sound. If the fans and compressors are roughly equal sound sources, the largest drop you can expect by treating the compressors or even turning them off is 3 decibels. If the fan contribution is greater than the compressors, the drop will be even less. Of course, this is unlikely because compressor and fans noises peak in different octave bands. And try to choose a firm that has prior experience attenuating similar equipment. It's helpful if they can provide before and after sound data for various attenuation options. Here's some examples of field retrofitted units showing before and after photos. Here's an air-cooled chiller with a helical rotary compressor. And here's an after shot of the compressor with a wrap around it and the refrigerant lines. Compressor attenuation without fan attenuation can be useful if the compressor is much louder than the fans or when it seems louder because of poor sound quality. So here's an example of another air-cooled chiller that has both compressor and condenser fan attenuation. Notice the compressor and the refrigerant lines are wrapped. Also, note the large structure being built around the chiller. Here, you can see the final, complete product with silencers. Remember that existing equipment may not be designed to support the weight or wind load of added attenuation. Also, realize that sound radiates up and down from the condenser fans. It will exit through the coils and out of the open area underneath the coils. The silencers will only attenuate sound going upward. Finally, the addition of the silencers may affect equipment performance. If airflow is restricted, to quiet the downward radiated sound, it's also necessary to add attenuation to both the open area around the bottom of the unit and the coil surfaces. Here's a unit that has louvers installed. A subset of quieting the source is to change the type of source. There are times when attenuating the unit to meet the requirements will be prohibitive. In these cases, it may be that a different type of unit is needed. Switching from an air-cooled chiller to a water-cooled chiller is an example. Another example is to use a split system. Separating compressors and fans allows the compressors to be placed either indoors or in a bunker to attenuate the radiated sound. One example is to place an air-cooled condenser coil inside an air handling unit designed with quiet fans and sound attenuation to meet the project sound goals. This will reduce unwanted noise, but it will increase system complexity and first cost. Sometimes, these units are designed to be used indoors or outdoors.
But that sounds like something that should be done before the equipment is installed.
Definitely. it might be wise to make an acoustical model at the same time energy models are being made to select equipment. Another option is to increase the distance between the source and the receiver. Typically, this option is rejected due to the inconvenience and perceived high cost of relocating the unit. During our air-cooled chiller example earlier, you might have wondered how power and chilled water were expected to be distributed to and from the unit. And a relocation alone may not provide sufficient reduction, but it should be reviewed. The next option is to add a barrier to obstruct the direct path of sound from the source to the receiver. It can be something natural, like a hill or earth berm. Sometimes you'll see these used along highways, but most often a man-made wall is used. Some or several rows of trees or landscaping provide a visual barrier, but little or no sound attenuation. Equations are available for calculating the effect of the barrier wall, and there's a table of insertion loss values for solid barriers in the HVAC Applications Handbook published by ASHRAE. So a barrier wall can be installed between the sound source and the receiver. Designers have the flexibility to place the barrier in various locations and adjust the height as needed. But be aware that placing a barrier close to a unit can disrupt airflow through the coils. Consult the manufacturer for minimum clearance requirements. The key factor for determining the effectiveness of a barrier is the difference in length between a direct line from the source to the receiver compared to the actual path sound will take to reach the receiver over the wall. More attenuation will be provided by the barrier as the total path length difference, line segments A and B, increase over D. As the barrier height changes, the total distance of paths A and B increase over D, which increases the attenuation of the barrier. Taller barriers increase sound attenuation. So let's put some numbers into this example. Here, the total linear distance from the source to the receiver, or D, is 33.6 feet. But the sound must actually travel over the 10-foot barrier along paths A and B, or a distance of 14.5 and 20.1 feet, respectively. Plugging this into the equation yields an answer of 1 foot. So let's move the barrier closer to the sound source and recalculate A and B. The total distance D remains the same. Path A is shorter, but path B is longer compared to the previous example. This results in a greater path length difference with a computed value of 2.6 feet. Looking at both examples together, you can see the total path length difference is greater in the second case where the sound barrier is closer to the sound source. So here's an excerpt from Table 39 found in Chapter 48 of the 2015 Handbook of HVAC Applications. This table shows insertion loss values by octave band for various path length differences. In our first case, with the barrier midway between the source and the receiver, we computed 1 foot. And in the second case, we computed 2.6 feet, which I'll truncate to 2. The resulting insertion loss values are certainly more favorable for the system with a barrier closer to the sound source. So what if we put a vertical barrier into our school example? Last time, we were right at the sound requirement with some factory attenuation. With a 10.5-foot vertical barrier installed between the chiller and the practice field, the insertion loss can be computed and added to the example. I computed a path length difference of 1 foot with this barrier. The corresponding insertion loss values were added to the previous example, a chiller with some factory attenuation. The result is 39 dBA, which is well below the lot line requirement and probably makes the practice fields more pleasant. This is one of those scenarios where you might want to work the source path receiver process backwards. Start with the receiver target sound pressure and the source sound power, then compute the distance correction. Additional needed attenuation will establish how much insertion loss is needed, which determines the path length difference, and that drives the height of the barrier.
So with the barrier and distance correction, we now have 2 components that make up acoustic attenuation. I can see how this could start to get complicated. Can software be used for an acoustical analysis?
Yeah, there are several different software programs available to make predictive calculations. The Trane Acoustics program, or TAP, uses the source path receiver model for acoustic modeling. The user can enter sound power data, describe the sound paths, and TAP will provide sound pressure at the receiver location. So let's use TAP to make a model of the air-cooled chiller next to the parking lot and practice fields. I'm going to move over to the monitor and demonstrate how simple it is to make this predictive model. We'll start with the TAP program running. Notice the program is divided into 3 sections. The path view sits at the top with the sum view in the middle and the path table view at the bottom. The path view is where we'll enter sound source data and build the various paths sound takes to reach the receiver. TAP already has sound data built into it for some equipment, but it's easy to enter sound power data for any piece of equipment. I'll choose Custom from the Elements menu. Here, I'll enter sound power for the chiller. I'm going to start with the first case where a standard chiller is being used. I can provide a descriptive comment if needed. When I click OK, the window will close and we'll have a sound path in the path view section. Also, notice the TAP is already performing calculations in the path table view. Next, I'll need to create an outdoor correction to account for the distance between the source and the receiver. I'll choose Outdoor from the Receiver Sound Correction portion of the Elements menu. Here, I can specify the height of the sound source, the height of the receiver, and the linear distance between them. We'll use some of the other features next. Again, I can enter some descriptive comments. I'll click OK to save the data and return to the main screen. Notice the path view table has updated with our sound power to pressure distance correction. TAP reports the octave band sound pressure and A-weighted sound pressure. Recall that the manual distance correction resulted in -42 in each octave band, and TAP computed -43. This difference is attributed to rounding. The result was higher than our ordinance at 55 dBA, so the next option was to specify a quieter chiller. We could repeat the whole process again, or we could copy the path and change the sound power data. So here, I'll just copy the path, update the path description, and change the sound power data. The results are displayed in the table view section. Like we saw with the hand calculation, the A-weighted sound pressure data is close to the code maximum. Because of this, we added a vertical barrier between the source and the receiver to deflect some of the sound from the lot line. Adding a vertical barrier in TAP is pretty simple. In our copied path, we can adjust the description then open the Outdoor Receiver Sound Correction element. Here, we'll toggle the barrier, enter the distance between the sound source and barrier, then enter the barrier height. I'll click OK to close the window, and we can see the predicted result. Just like the hand calculation earlier, the predicted dBA level is much lower than the ordinance.
The hand calculation and the software calculation yielded pretty similar results.
They did. TAP doesn't use the exact same calculation we showed earlier, but it's nice to see similar results.
TAP makes it look pretty easy, but I'm sure there are some limitations. Of the 2 choices, quieting the source or quieting the path, quieting the source is a good choice.
That's right. It's especially useful if the factory attenuation options have been tested and sound data is available. The quality of construction and installation details are not factors. The quieter unit will benefit other receivers even if not required. And if renovation or future construction occurs, the quieter equipment will be easier to deal with.
Modifications in the field introduce some additional uncertainty, but might be a good option either as a standalone treatment or in combination with a barrier. Dave, the distance correction with a barrier seems pretty simple, but I'm guessing there are some complications. For one thing, what kind of wall are we talking about? Does it have to be built from specific materials?
The best way to answer those questions is to look at what the barrier wall calculation includes and ignores. The slide shows a sound source and receiver separated by a barrier wall. Some of the sound leaving the source is reflected by the barrier. A portion of the sound is transmitted through the wall and a portion is absorbed by the wall. What is left is the sound that goes over the barrier. A line connecting the source to the top of the barrier divides the area that will be attenuated by the wall from an area that is unaffected by the barrier wall, called the bright zone. Basically, if you can see the sound source from the receiver location, the barrier wall isn't providing noticeable attenuation. This is a good thing to keep in mind if the neighboring property is a high-rise or the properties are at different elevations. The area below the line is called the shadow zone. Barrier walls don't totally eliminate sound in the shadow zone because diffraction occurs when the sound waves hit the top of the barrier. It's the diffracted sound that's being calculated by the barrier equation. There's one more quality of diffracted sound to consider. The amount of diffraction is frequency dependent. High frequency sound doesn't diffract very much, but low frequency sound is able to bend around the top of the barrier. What that means in practice is that the barrier attenuation is not the same for all frequencies. If you look back to the barrier calculation Eric did, you'll see that the attenuation provided by the barrier was 8 dB at 63 Hz and increased to 22 dB in the higher octaves. Now let's look at what the barrier equation ignores. These are called flanking paths. The first flanking path to consider is sound going through the wall. The barrier equation assumes that sound going through the wall is insignificant compared to what goes over the wall. The drop in sound going through the wall, called transmission loss, abbreviated TL, is dependent on barrier material. Transmission loss generally increases as the mass of the wall increases. And for all materials, transmission loss varies with frequency. Lower frequency sounds are more difficult to block, so the transmission loss will be less. Bottom line, the wall must have sufficient transmission loss at all frequencies so that the sound going through the wall doesn't add to the sound going over the wall. At grade level, barriers are often made out of masonry of some sort, but can also be made out of prefabricated panels. This slide shows before and after photos of a barrier wall constructed of prefabricated panels. You can check to make sure that the sound going through the wall doesn't contribute to the sound going over the wall by determining the sound pressure level on the source side of the wall and then subtracting the transmission loss of the wall. An important step in this process is to calculate the composite transmission loss for the wall. The composite transmission loss accounts for variations in the wall. For example, adding a door that has a lower transmission loss than the barrier will reduce the overall transmission loss, as will any gaps or airflow bends. Gaps and openings have a transmission loss of 0 at all frequencies. To calculate the composite transmission loss, you'll need to know either the transmission loss or transmission coefficient for each of the various components. Transmission loss and transmission coefficient are related by the equation shown on the slide. And the transmission coefficient for the composite panel can be determined as shown in the second equation. Here's an example. An 8-foot tall, 20-foot long barrier panel with a TL of 40 dB is placed between the source and the receiver. Final grading results in a 3-inch gap between the bottom of the panel and the ground. Running this information through the equation results in a composite transmission loss of 15 dB. That's a serious degradation from the 40 dB of the original wall material. Small gaps can cause large reductions in sound transmission loss. Notice that this is true for any type of barrier. Sometimes compressors are enclosed by panels or an acoustical wrap to reduce radiated sound. The little gaps where pipes, wires, or supports leave the enclosure don't look very significant to the eye, but they can drastically degrade the performance of the enclosure. Here's a graph that shows the impact of percent open area on transmission loss. The x-axis is transmission loss of the panel without any openings. The y-axis is transmission loss with the openings. The curves on the graph represent percent open area in the barrier. It does a good job of showing how an increase in percent open area results in a decrease in the amount of transmission loss. As percent open area increases, the actual attenuation of the barrier decreases. In the example, the barrier had a 40 dB transmission loss and a 3-inch gap was about 3% of the total wall surface. Also notice the area where the percent open curves become horizontal. Once you've hit the flat portion, increasing the TL of the panel will not improve the composite transmission loss. Improvements will only come by reducing the open area. The second flanking path that is ignored is sound going around the ends of the barrier. It's typical to focus on sound going over the top of the barrier wall. But if we look at the barrier in plan view, it's clear that sound can also go around the ends of the wall. The barrier equation doesn't account for sound going around the ends of the wall. So the wall must either extend a sufficient distance beyond the end of the unit or wrap around 3 sides to prevent a contribution from the end-around flanking path. The final condition to watch out for is the 4-sided barrier. I think people figure as long as they're putting a barrier on 3 sides of the unit, they might as well add the 4th side. This causes a problem because the barrier wall calculation assumes that the sound reflected from the barrier does not contribute to the sound at the receiver. Adding walls all the way around the unit creates a reflective surface that redirects sound reflected from the barrier back toward the receiver. The 4th wall also reflects sound from the opposite side of the unit toward the receiver. Both of these sound paths add to sound at the receiver location that is not accounted for by the barrier calculation. In some cases, it's not possible to leave one side of the barrier open because there really isn't a direction that's not sound sensitive. Other times, the 4-sided barrier effect happens because the unit is placed in a pit area. This slide shows before and after photos of sound absorptive material being added to the inside of the walls surrounding the unit. The photo on the left shows the unit surrounded by highly reflective painted block walls. Weather-resistant sound absorptive liner is permanently attached to the walls. The addition of acoustically absorbent material to the walls will reduce the amount of sound reflected from the wall. I realize that was a long answer to what seemed to be a pretty simple question.
It sounds like how the wall is constructed, both the shape and the quality, are just as important as the material. Thanks, Dave. Eric, suppose I've looked at the sound reduction options for the unit and a well-constructed barrier wall, and I'm still exceeding the target set for the job. Is there anything else that can be done?
Occasionally, we do run into cases where an extremely low sound target has been set or equipment was placed without regard to sound, and all the common solutions don't provide enough attenuation. It's often possible to quiet the equipment on these jobs, but it's not cheap. Most outdoor HVAC equipment uses ambient air for heat rejection, so the entire unit can't be easily enclosed in a large sound enclosure, unless some accommodation is made to get air in and out of the box. As Dave just pointed out, simply cutting openings in the box won't work because this drastically reduces the transmission loss of the structure. Adding acoustical louvers to the openings can help, but the attenuation of the louvers is limited and they add pressure drop. In most cases, the fans supplied with HVAC equipment are sized for the pressure drop of the coils. Additional pressure drop reduces flow and may overload the fan motors. Of course, all this should be done in coordination with the equipment manufacturer and an acoustical consultant. The solution in these extreme cases is to duct the air in and out of the box using additional fans and duct silencers. The fans can be sized for the pressure drop of the silencers. In some designs, the original propeller fans on the unit are removed, and in other cases, they stay in place. It's not an easy fix. Here are some things that must be considered if you go this route. Service access. Maintenance and monitoring of the equipment requires access to the equipment. There must be a way for personnel to enter the box and room for them to work inside. There must be room inside the enclosure for the outdoor air to move around the coils evenly to avoid degrading unit capacity. And the structure must be designed to avoid recirculation of air through the coils. The enclosure with the additional fans, silencers, and room for service and airflow will be significantly larger than the original unit. The added fans will need to be integrated with start and stop of the unit. In addition, most HVAC units change airflow with load. This requires the added fan to be capable of variable flow and coordination between the added fan and the unit controls. It's easy to see that this is an expensive solution. In many cases, the attenuation will cost more than the original unit. With these things in mind, you can see that this is a last resort.
That highlights the importance of doing the acoustical model before the equipment is installed. It could be that outdoor HVAC equipment was used to reduce installed cost, but having to build an enclosure like you just described might make an alternative system type more appealing. Thank you both for sharing your thoughts and ideas on outdoor HVAC acoustics. Now let's summarize what we covered today. There are several different ways sound ordinances can be expressed by jurisdictions. Depending on manufacturer, factory designed and tested attenuation can be provided or equipment can be modified in the field. The source path receiver model allows you to analyze sound sources and determine what the sound level will be at the receiver's position. Vertical barriers, when properly designed, can provide good sound path deflection and attenuation. And sometimes designers must get clever with enclosures or unique types of equipment when meeting sound requirements are a challenge. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or download a free trial of Trane Acoustic program at trane.com/TAP. For those of you seeking continuing education credit, be sure to check out our continuing education programs, which include many past ENLs, all free and on demand. And don't forget to fill out a survey and let us know what you think of today's program. AIA members, turn in your member information to your local site coordinator. Finally, please ask your local host about details for the 2017 Engineers Newsletter Live programs. Thanks for your time today. We look forward to seeing you next year.